CLion a cross-platform IDE for C and C++. Download now.
Welcome to my session in cplusplus 2025. My name's Anthony Williams. I'm going to talk to you about writing a base level library for safety critical code. Just a little bit of background, then obviously I've been talking at conferences for a number of years, so some of you know me. I wrote a book on multi-threading, C++ concurrency in action, and currently I'm working at Woven by Toyota, writing software for Toyota cars. And that's been an interesting journey, and I'm going to talk to you about some of the things involved in what we're doing there. So just as an overview of what we're going to be covering, so next hour and a half, then I'm going to start off. I'm going to do an introduction to the library, what we're going to be talking about today. I'm going to talk to you about the various standards that we have to conform to for the code that we write in order to actually successfully manage to deploy it on vehicles. I'm going to talk to you about the sorts of tooling that we use in order to make it all work. I'm going to talk to you about the testing that we do, and the error handling that our approach to error handling, the impacts on the design, for how the standards conformance and the error handling and the testing that we want to do, how that affects the design of our code. And then I'll finish with a brief summary with some overall thoughts. Okay, so introduction. The basic idea is that modern cars contain a lot of computers. They tend to be called electronic control units, ECUs, in cars, but fundamentally they're just small computers. And modern cars have hundreds of them. They're data centers on wheels, moving around, doing a lot of processing. And lots of these are they're in control of the things which are vital for safe operation. Once upon a time, then the digital electronics in cars would have been, things like the radio. But nowadays, then it's not just the radio; it's the entire cockpit display. And so, if that doesn't work, then you can't see how fast you're going and things like that. But then, not only that, but the actual control of the engine will be by an ECU. The actual control of the brakes or the steering. Well, no longer is there a direct physical connection between you pushing your foot on the pedal or turning your steering wheel. It actually all happens via a computer in the middle. So there's a heck of a lot of software, and lots of it, therefore, is vital for safe operation of the vehicle. And actually, in practice, a heck of a lot of this stuff is written in C++. There's still a fair amount of C, and we are seeing a few bits of software that are written in things like Rust. Some of it's still written in assembly language. Some of it is generated from higher level models, but in which case then it's often generated C code that's then compiled down. But of the handwritten stuff, lots of it is actually written in C++. And certainly, all the software that I personally work on for our vehicles is written in C++. And in fact, the code that my team writes is intended to be usable by all the C++ code in the vehicle. We're writing low-level libraries that we're hoping that abstract lots of the things like data structures, and that then are common to lots and lots of the code in the vehicle. And so our code consequently then needs to make sure that it conforms with all the appropriate safety standards and specifications, whereas some of the because eventually it does, if we're intending it to be used for all the C++ code in the vehicle, that includes those things which are necessary for the safe operation. Whereas other parts of C++ code might not be necessary for the safe operation. And so just for the sake of clarity, because people talk a lot about what we mean by safety in C++ at the moment, specifically when I'm talking about safety and safety critical software, I am meaning software where the consequence of failure is potentially injury or loss of life. And obviously, that's not specifically cars. Obviously, like I said, we know the software that controls the drive chain, that controls the brakes, controls the steering. Clearly, if that goes wrong, then there's potential for injury or loss of life. But it's not just cars. It could be, software controlling medical devices. It could be software controlling the air traffic control software for airplanes. It could be the signaling software on railway lines. Any of this software is where the consequence of failure is injury or loss of life. And this is distinct from things like banking software, where the downstream consequences might be bad. If people can't get their money, then there might end up being injury and loss of life, but the immediate consequence is not. So there is that somewhat distinction. And obviously, games and office software are complete other. And if you can't play your game, then you might get cross. It's not going to be a big problem. And it really does. It impacts how we develop software. There's the thought that if this goes wrong, then somebody could die. It sits there in the back of your mind all the time, and so you have to consider everything. You have to think, what if this goes wrong? What are the effects of the errors in my code? Having thought about the errors, you need to minimize the chances of them ever happening anyway, which you can't always do, but you do need to minimize those chances. Having thought about the errors and minimize the chances, then some of them are still going to happen. So we need to defend against the bad effects, make sure that the consequences are as minimal as possible, so that so that people don't die, they don't get injured. When we hope that what happens when our software goes wrong is that either the software seamlessly recovers from the mistake, or B, you get a warning light on the dashboard, and that beyond that, the consequences for the driver are somewhat minimal. So that's what we're aiming for. We're always trying to defend against the bad effects. And then, because we are, it is the industry as a whole is regulated, then having done all your analysis and done your work of minimizing the chance of errors and defending against their bad effects, you need to document this, provide evidence. And so lots of what we do is about providing evidence for the safety case, which is the totality of the documentation that you submit to the auditor from the regulatory body to say, we think this is safe enough to put on a car, or safe enough to put in the medical device, or safe enough to manage the train signals or whatever. And so, that is the safety case. The argument that this is safe enough. Okay. So before I'm going to move on to talk about the standards, but before I do so, I'm just going to say, if anybody does have any questions as we go through the talk, then please feel free to ask them using the Zoom Q&A feature. And when I become aware that there's a question, which I won't immediately notice necessarily, but when I do, then I will do my best to answer the question. Alternatively, then you can save up your questions when we can deal with doing gather town at the end of the talk. So either way works for me. Yeah, as we go through, then yes, I say so. If I notice that somebody's asked a question through Zoom, then I will do my best to answer. Otherwise, yeah, way too count time. But now let's talk about standards. And when we mean safety critical software, there are two sorts of standards that we care about. There are standards that cover our development process, and then there are coding standards that affect the actual, the code that we write. And they are distinct, because the process standards tend not to be programming language specific, whereas obviously the coding standards do tend very much to be programming language specific. So pretty much all the process standards for safety critical software uses their baseline IEC 61508, functional safety of electrical or electronic or program or electronic safety related systems. This is like the master standard that covers everything, and but then from that, then industries then tend to have their own specific ones. So for automotive software, we have ISO 26262. For aerospace software, we have DO 178C. For medical device software, there's a few standards I think are centered around IEC 62304. And then for railway software, we have Senelec EN 50128. In my personal experience has only been with the top two. I've never personally written anything for medical devices. I know people who have, and likewise, I've never written anything for the railway software. But other industries with which write code that is safety critical will also have their own standards, and so you're expected to conform to the standards relative to your industry, but they all tend to come back to IEC 61508 as the baseline, from where they get their terminology, the overall process descriptions and things like that. And yeah, these are process standards. They cover everything about your software development process. And so they cover requirements, how you document and specify your requirements. They cover the design of your software. They cover the testing of your software. But what they crucially don't cover is language-specific coding standards. Because this is a language or agnostic thing about where you develop your software rather than specific process. But on that side, what they will do is they will document the safety integrity levels, which is about the consequences of your software failure. So there'll be low-level things where this is the bare minimum of something where, well, it is something that can have an effect, but it's not going to be catastrophic if the software goes wrong. Where all the way up to, if this software goes wrong, then there is no way that it is not a problem. And so, if your brakes fail, then that's going to be big. If, on the other hand, the electric windows fail, not such a big issue. I'd say there's quite, and obviously and there are grades in between. And each piece of software is assigned a safety integrity level based on what it does and what the consequences of failure are, and then any external failure mitigation. So you might have some software that's controlling the brakes, but if there's if there's different bits of software that are involved, and there's sort of, well, if this one goes wrong, then we have a backup, then that can affect things. And so there might be some aspects of some of the software in that chain is then less crucial than others. And so depending on what failure mitigation consequent things you've got in there. And so, but ultimately, any given feature that is a software feature will have a safety integrity level assigned to it. And then the safety integrity levels then determine what the specific rules are that you then need to apply based on the safety standards that you're conforming to. So I'm in ISO 26262 for automotive, then they define automotive safety integrity levels, which are shortened to ASIL in lots of places. And then we also have QM stuff, which is quality management. And then, whereas if you're doing DO 178C for aerospace, then we have 5 design assurance levels or item development assurance levels, which again are the different levels of consequences and therefore the requirements on the software development process. And similarly, all the other standards are going to provide this similar definitions. They will have their own precise details on what the levels are, what they call them, how they're designated, but the idea is there will be a series of different levels which then have different consequences on your software development process, on the things that are required of you. And just something else that can get in the way is, if you're moving from one industry to another, and therefore these things can confuse you, is that sometimes they order them differently. Now, they might order them from 1 to 5, they might order them alphanumerically, and then which one is the most stringent order can be not necessarily obvious. In ISO 26262, then QM is the lowest level, and then ASIL A is the next one. And then it's alphanumeric, so ASIL B, and then ASIL C, and then ASIL D is the highest, most stringent level. On the other hand, with DA 178C, then it's also alphanumeric, but this time DALE is the lowest level, and DALA is the highest level. So we've got the alphanumeric, some in the reverse order to in the aerospace industry to the autospace industry and automotive industry. So that can cause a little bit of confusion if you're talking to somebody else or moving between industries, but it's not really a big deal. It's just something to bear in mind. And the higher the integrity level, the more stringent the requirements on your process overall, what you're and then as a consequence, the evidence that you're expected to provide to the regulators and auditors. So just as a concrete example, if you're doing automotive software and you've got something that's ASIL A, then it might be enough to just do a walkthrough of the design with the auditor. Whereas for ASIL D, then you will need to do detailed inspection and analysis and various documentation, and it'll be a lot more stringent. What's expected of you to produce as supporting supporting documentation alongside the actual software itself. And like I said, this is all then about the safety critical standards are about the processes, but then they also then defer the coding standards to safety critical coding standards, which are separate from so ISO 26262 doesn't specify anything about C++ code. What it does say is that you must have appropriate coding standards. And so we have to have a safety critical coding standard that we can use, which then will specify what language constructs you can use, how you use them, and things like that. And these are then developed by the specific industry alongside the regulatory standards, and they might be very specific. So, the AutoSAR C++14 coding guidelines, which cover automotive stuff. They sort of one such standard, and in this case, then we have a rule in 518-1, which says the comma operator shall not be used. It's very specific, therefore, if you're writing C++ code expecting to conform to these coding guidelines, then you can't use a comma operator. On the other hand, they might be far more generic. So the MISRA C++ 2023 coding guidelines they have the rule, this one, rule 6.01, block scope declarations shall not be visually ambiguous. And so that then leaves a lot of scope for what does it mean for two declarations to be visually ambiguous, and there's a lot less precise, and there's a lot more leeway in there for discussion. But in this particular case, it's like don't have variable names where the distinguishing between them is one's got a 1 and one's got an L, or one's got a 0 and one's got a capital O. Was the only distinguishing feature between them. And so it's fairly obvious what when you look at it, and sort of, well, is it clear what these two things declare and that they are distinct? But it still gives you scope for judgment, whereas the comma operator rule is quite unambiguous. If you have a use of a comma operator, then you're violating that rule. Typically, just in general, then the coding standards are, of course, going to lag behind the language standards. They are developed by the industry after the language standard has been ratified, and people have then had a couple of years experience using that language standard in order to work out what the pitfalls are. So, for example, the first MISRA C++ standard came out in 2008, and that covered the C++03 standard. So that was 5 years after the standard was published. The C++14 guidelines published by AutoSAR came out in 2017. So that was only 3 years after C++14 came out. So that's not too bad. Whereas the most recent C++ coding standard from MISRA, 2023 standard, was for C++17. So again, that was 6 years after the corresponding language standard. And in fact, we've had 2 more C++ standards since then. And C++26 has now just been ratified, and there won't be an automotive coding standard that covers that for a good number of years now. Yes. But there we are. I see that there is a question on the Q&A. See if we can see what it is. Okay, so yes. Question says, which C++ standard are you using in your automotive software development? We have safety critical guidelines relating dependency and platform dependent dependencies to move to the latest C++ standards. Just curious. So yes, the answer to that is that we are using a mix of C++14 and C++17 because we have codes that either must conform to the AutoSAR C++14 guidelines or the MISRA C++ 2023 guidelines. And so that is where we're at. And at the moment, then that is mostly the say everything has to conform with C++14 still. The C++17 standards. And the standard itself for MISRA was only published in 2023, and as we'll see in upcoming things, then we're relying on tooling that then needs to help us check our conformance to the coding standards, and so that then takes further time before the tooling is available. So we're always lagging behind. So if you're conforming with the process standards, then that then requires that you have coding guidelines for any used programming languages, and so then you have to pick a industry coding guideline when it's applicable that then you can use. And this, as just described, it does limit the use of newer language standards until there is a suitable coding guideline. You do have the option of writing the coding guideline yourself. So you could say, yes, we're going to use C++23 today, and we're going to write a coding guideline for it. But then that means you've got to argue for each and every language feature. You've got to argue why it's safe, why you put whatever restrictions you have on things. And that's a lot of work. And doing it in sufficient detail that you can convince the auditors that you've thought of everything in order to conform with the regulations is hard. So it is most straightforward, and therefore what most people do is to choose one of the industry standard coding guidelines for whatever industry you're in order that then you can say, well, people have thought long and hard about this, and the industry as a whole has approved it. And so from when you're talking to the auditors, then you can just say, look, we follow the industry coding standards, and they can say, okay, that's good enough. Whereas if you write the coding guidelines yourself, then you have to argue about all the details and demonstrate that you've thought of things in sufficient depth. Okay. So on to tooling. We can't just use anything when you're writing your code. You have to think carefully about what the consequences are. And so anything that affects the generated code or your verification and validation, it needs to be suitably qualified. So we can't just say, oh, well, yeah, we're going to use the latest version of GCC or Clang, because off the shelf, it hasn't been qualified. You can't just decide that you're going to just use whatever checker you like to verify that you're conforming with the coding standards. You have to use something that has been through the appropriate qualification steps. So yeah, this obviously the compiler, the first thing. If the compiler generates bad code, then the code that's running on the car isn't necessarily going to be what you intended. And so we need to qualify that compiler to make sure that, yes, it's been suitably tested, and it is actually going to generate code that does what you tell it. If you have a code generator, so if you've chosen to do some form of model-driven development where you use a MATLAB or Simulink model and then generate some code, then your code generator needs to be qualified to demonstrate that the generated code matches what you've put in your model, and then so that then again what goes on the vehicle actually is what you intended. If you have a static analyzer, then it needs to be verified, qualified to say that yes, it does analyze what it says it analyzes. And if you have violated a given rule that it says that it checks, then it will tell you. And then anything that you use for testing tools then also need to be suitably qualified. And again, the level of detail that you need to put into this suitable, this qualification, again, depends on quite what the consequences are. While testing tools require much, and static analysis requires much less detailed qualification than the compiler or code generator would do, because they don't affect actually what the code does. They're just about checking and about generating the evidence. And so that is, has less consequence, but it's still important that you've gone through the process and things have been suitably qualified. In ISO 262, 262, then we have there's the idea of the tool confidence level, the TCL, which is about what's necessary for how important is this tool to make sure that the software is running correctly. And again, like the ASIL levels, the different ASILs for how serious the effects are, and there's different TCL levels for what the consequence of the tool going wrong would be. And so the specific qualification requirements, they will depend on the safety integrity level of the software. If you're, if the software for controlling the radio or the electric windows, it can go wrong much more readily than the brake software, and so therefore it doesn't matter. You don't have to think so hard about whether your compiler got it right. The same as you don't have to think about whether you got it right when you're writing the software. And then the consequences of an error being introduced by the tool. So again, if the compiler goes wrong, then the consequences are that your software actually does the wrong thing. Whereas if the static analyzer goes wrong, then it just doesn't tell you about something that you may or may not have done. It doesn't directly affect the behavior of the software. And I'm going to stop there for a second because I see that there's some questions. So first question is, does that include qualification of unit testing tools as well, or is tool qualification based on ASIL level of the software component in which it is used? So yes, and to an extent, it does include unit testing tools. And yeah, and hopefully, yes, hopefully you'll this is being addressed by what I'm talking about now, is that the tool qualification depends on the ASIL of the software component that you're developing. But yeah, if you have your unit tests and you're running your unit tests and the testing tools do it wrong, and then tell you that you've passed when your test passed when it failed, then that obviously means that you don't know that the code you've written is actually behaving correctly, and that therefore can be a problem. So you do need to qualify your unit testing tools as well. And so we have another question, about why something like the static analyzer should be approved. And this is, I understand when we talk about the compiler or libcc, that analyzer just checking the code and not affecting what might be released, even if the analyzer works incorrectly, catching novel cases or having false positives. It doesn't affect safety in your terms. And yes, you're right. And so that's why the confidence level that's required of a static analyzer is less than would be for a compiler, because the consequences are less bad. But it is something that needs checking, because if you're relying on it to check that you are conforming to your coding guidelines, and it doesn't pick things up, then you might have written code that doesn't conform to the coding guidelines. And the reason that the coding guidelines are there is because particular coding patterns have the potential for introducing problems. And so it all comes back down to, and so then so if you can't rely on the analyzer to have done it correctly, then you have to do the analysis by hand, which is then more tedious. So so you need to therefore expect it to be working, and so therefore it needs to be suitably qualified. But it is less stringent a check than if it had been a compiler. And so then obviously the final thing that you do consider when you're doing your tooling qualification is, what is the chance of an error going undetected? If the if the way that your compiler goes wrong is that it fails to compile your code, then you're going to detect the problem fairly quickly. Whereas if it silently generates incorrect code that is almost correct but not quite, there's does some floating point calculation that is that has a larger error than documented, or if you put in specific values, then it gives you the wrong answer, then that's obviously quite a bad thing. And so, then you're looking at, well, what are the error chances of it going undetected? And so then that comes back down to testing, and more testing. Because overall, then so both of the tool itself and of your software, because the more that you test your software, then the less you're relying on the documentation provided by the tools in terms of their qualification levels and things like that. So yeah, so obviously one of the most important tools that we use is a static analyzer, because the coding standards have lots of rules, and enforcing them by code review is tedious and error prone. It's bad. If you're reviewing a PR that somebody's made that's a few hundred or thousand lines, then checking that it does what it does, that it's reasonably well designed, does what it's supposed to, it's reasonably well designed, has good tests. That's one thing. Checking that it also conforms to all 500 rules from your C++ coding guidelines. You're not going to remember all the rules by heart, so you're going to have to then refer back to the document, and doing that for every line of code is just tedious and error prone. You're going to miss something. You're going to miss one of the rules. You're going to misapply it, not notice that the code has changed. So having a static analyzer that's going to do that for you is very, very important. So yeah, static analysis tools are essential. It is not practical to generate significant sized safety critical code without them. And so consequently, we run static analysis in our CI system. You cannot merge to main unless the static analysis passes. It's just hardwired there as part of the system, and because it's so essential. Well, and obviously, it's important also to be able to run it locally. It's slow running the static analysis, depending on which tool you're using. Then sometimes, on our particular code base, it might take anything between 20 minutes and 4 hours. And, so doing that on every time you make a change is slow. But it can be better to run it locally rather than waiting for CI, where you've got to wait for it to get queued up. You might have to wait for the CI job to wait for some of the other jobs to succeed, or and things. And so you can, and it helps make it a bit faster if you can run it locally, but it still doesn't get over the fundamental fact that as your code base gets bigger, then the static analysis takes longer. Because it does just scale with the size of the code base. And again, depending on the tool and the checks that it's doing, it might scale more than linearly, so that it takes more than twice as long if your software is twice as big. Which is unfortunate, but it's just the nature of the beast. So we're always trying to improve, do things that can make our CI run faster, so that we don't have to wait so long. But it is one of those things that's just important. And part of that is that the CI analysis result then becomes part of our safety case. So we can say, yeah, we conform to the safety guidelines because this piece of software, which is qualified software, has told us that we conform. And so that's why the qualification level on your static analyzer is important. If you can't rely on its output, then you can't then use it for your safety case. And then the auditor then says, well, how do you know you're conforming to your coding guidelines? It's like, well, we rely on this tool which we can't rely on. So, okay, well, then we have to audit everything ourselves. So it needs to be qualified. but this comes under just a general guideline. No, it's a required check, and so we need to automate it. It has to be part of the CI system. Like doing your automated tests. If it needs to be part of the final deliverable, you need to conform to these standards, then you need to automate that, because doing it otherwise is just too, it's too bad, too slow. Certainly, I've seen some of the teams that I have seen teams where they are trying to conform to the automated coding standards, and they write some software and then they apply the coding standard. And they might still use a static analyzer, but if they haven't been using it going along, then you've now got 10,000 lines of software, or maybe more, maybe 100,000 lines of software, and now you're running a static analyzer, and it'll tell you that half of your lines are now wrong. There are too many things which you don't internalize, because if you until you've been working in the industry for many years, and so you and even when you think you've internalized it, then you just you end up not writing things that in conformance with the coding standard by default. You think as developers we write too much other code, it doesn't have to conform. So you read too much code. You go to a conference talk and people show you stuff. Oh, we can do it that way. It's like, yeah, but the way that you're showing on the example won't meet the coding standards. So you don't then automatically write it that way. And so if you leave it to the end of the thing, then it then takes months, as you have to go back and you have to change all this line of code, which now has been changed. And so now needs re-reviewing it, now needs retesting. Doing it at the end is bad. So we automate it. We do it as part of the CI system. You're doing it all the time. Every time you make a change, we check with the static analysis. So this is it's a very important part of the process. Which then brings us on to testing. And you can't just review the code and say, yeah, it looks good to me, ship it. No, you have to actually demonstrate that it does indeed work. We are definitely not in the realm of move fast and break things. It is very definitely move slowly and make sure that nothing ever breaks. And in order to make sure that nothing ever breaks, you have to verify that it really does what's intended. And that means testing. And testing, and testing. And maybe a bit more testing. And of course, automated testing for repeatability. So I made on my code, I've changed the line. Okay, what's it broken? How do I know? I run the test again and see and verify and provide evidence that I can then submit to the auditors as part of the safety test. So it's all very important to do our testing and make it automated so it's repeatable. And you can say, this version, look, this is the version that went on the car last year. We will take the software out of CI, we will rebuild it, we will rerun the test, say, look, here we are, it passed all the tests. So you can verify that everything has the behavior that you're expecting. We have another question. Mr. K says, I am curious about the dev setup used at Woven. Can you list all the tools used? See package manager, compiler, build tool, static analyzer, test libel tool, and any other tool. So yeah, and the short answer is a lot of different things. For package managers, then we'd use things like Artifactory for storing built intermediates. We use Bazel, we use CMake. There's a whole bunch of things. Compilers, then for on the hardware, then we use whatever the platform requires. For testing and development and things, then we use GCC and Clang, but we use a dozen different versions, because often the closest things to what might work. For build tools, then again we use a variety. I mentioned but for new stuff from my specific team, we use Bazel, but other people use CMake, and then another team was telling me that they were using like whatever it is that Android Automotive uses, because they needed to integrate with that. So there's a whole bunch of things. Static analyzers, then we use a whole bunch. CodeQL, C++ test from Parasoft, Coverity. I think there might even be some others in there. So yeah, there's a whole bunch of things we use, and all sorts of things. But actually, Woven it has a lot of developers and on a lot of different projects, and we end up using a lot of different tools across all those things. Particularly because the technology is different in different parts of the system. The testing for the things that are going to go in the car dashboard is going to be quite different, and the build system's quite different to the stuff that's building, running on the brakes and drive chain systems. So we end up with different compilers. It's a different operating environment, and different sets of things. So I hope that addresses some of that question, and we shall move on. So yeah, testing coverage. See, you've written some software, and ideally you want to say, yeah, we've tested 100% coverage. But then, of course, you have to say, well, what does that mean? And there's lots of things that people say when they mean coverage. Line coverage. Every line is covered by a test. Obviously, in C++, then you don't need lines. I can write my entire program on one line. It'd be a very, very long line, but that's one. So I've got 100% line coverage because, of course, that line's covered. So you might want to split it up into statement coverage, or you might just decide, well, you want to split your statements up so there's one statement per line. But it's still, somewhat of an issue. But assuming that you do split things up, then the basic idea is that if you have a function and it's got an early return, then anything after that return is then not covered. I ran my test. I call it field 1 and 2, and that first A is less than B, so we return 0, and then that the line that does the plus is not covered. So we need another test. But that can be tricky because if you've got something, you've got a switch statement, and then you're trying to you've got a default case, which might be required by your coding standard that you have a default for every switch. Then if your inputs are guaranteed to actually only cover the appropriate values of your enumeration, then you might not ever actually be able to write any code that reaches that invalid case. It's a backstop. What do I do if something really bad happens type? Well, if my data gets corrupt and I've got a bad value, then it won't actually do the red things or the green things, so I have to create an error somehow. And so we have to have a switch case, a case for that. But if get color only ever returns red or green when it's working correctly, then you can't construct anything that's going to do that, and you're not going to achieve your 100% test coverage, because every invalid color line will never be reached unless there's something that goes catastrophically wrong when you get data corruption. So that can be tricky. Well, and then the next sort of level of coverage is you want 100% branch coverage, where every branch is covered by a test. In the simple case, then we've got our if A is less than B test, then in this case we don't do an early return. But if we only call with function switch that if is running, then our else branch is not covered. With our one test here, we've got call bar with 1 and 2, and our else branch is not covered. So even though you haven't explicitly written it, it's still going to be a branch in the code. And so you need to consider what happens there, because the behavior is going to be different. You put the if there because the behavior will be different depending on whether the case is true or false. So you need to actually test it in circumstances under which that condition is both true and false. And so mostly that just means adding extra tests, but it is something that you need to think about. And sometimes then it can be hard to write a test that gets to things where the condition is deeply nested somewhere. For complex conditions, then often one tests modified condition decision coverage. Now, often people describe this as MCDC testing, but it's really MCDC. The way the acronyms go. It's it's the condition or decision in the middle. There's the slashes on. And it's about ensuring that all aspects of complex conditions are checked without doing exhaustive combination checking, because in a complex condition, exhaustive checking is just makes things too tricky. The number of conditions to check goes up, and it doesn't necessarily have enough different consequences to make it worthwhile doing that. Okay, so if we have our single lines, we're going to get 100% line coverage, whichever way things come out. But we've got three conditions, basic conditions. We're checking A and B and C, but we've got we're looking for if A is true and either B or C are true, then we do foo. Otherwise, we do bar. So that's what what our code is written to do. So what are the possible conditions we need to consider? In this case, we've got three possible Boolean testable things coming in, and so that is 2 cubed, which is 8 different options. But actually, there's only 2 outcomes that we care about. The overall condition is either true or false, and so though we've got a lot of those eight possibilities, then they get reduced to 2 at the end. And obviously, if you've got 4 options, then that then becomes now 16 different things to check, but actually you still only got 2 outcomes. So it's like the modified condition decision coverage is about reducing that coverage space. Okay. So I have another question about static analysis. It says, do you find you have branches that may permit lower levels of analysis for speed development and then have more stringent testing on release and merge into main? Or do you try and ensure every commit conforms to the entire suite of analysis? And we always try to confirm that everything conforms to the entire suite. It is, I certainly, yes, whenever you're merging anything to main, then it needs to be 100% perfect. But yeah, you don't run all the checks all the time. If you're doing local development, then you might you run you check out the branch from main, create a branch from main, and obviously it does conform to all the things. But then you're running. You're running your tests and you're making the changes, and you do a sequence of changes, and you might not run the static analyzer at all until you've done a number of changes, or you might stick to just running something simple like clang tidy that will pick up some really obvious things, but then not and then run the full analysis when you're done. Because it takes longer and interrupts development. So it's but then obviously when you go home at the end of the day, then you can push things to CI and let the CI do it. So then you can pick up in the morning and say, oh well, I've done things. The stuff I did yesterday, well, there were, as well as any new features I wanted to add before I pushed it, then there's also these static analysis errors that I can fix. So it's sort of a mix and match, but yeah, nothing gets merged to main until it's tested, and we try and do smallish PRs so that there's never anything that's too big. And then on code coverage, which is what we're talking about right now, then Honey says, which are the code coverage tools do you use? In our experience, some coverage tools can't identify some compiler generated lines. Examples when exceptions are enabled. Can you share your thoughts? Do you use code coverage exclusion markers in a production code? And yeah, we most of the time during development, then we use either gcov or llvmcov for doing the code coverage, and sometimes there are bugs in those, and that can be a problem, and so you have to document that, yeah, well, this file doesn't report as 100% coverage, even though everything is covered because the tool missed something. And that can be a pain, but we've automated means of marking up to say that. And yeah, actually in practice, that we don't tend to do that with exclusion markers in the source code, but we do have sort of auxiliary files that to document that. But then the final tests are done. You run the test on hardware with a special tool, which name I can't remember off the top of my head, to check the coverage on the target hardware, which is not just what GCC and Clang say when running in CI. So yeah, it's a separate thing. Okay, how often do we need to deal with false positives in static analyzers? Just to fix them or bypass some Tron rules because it's mandatory to have 100% parser checks? And the answer is all the time. The static analysis tools are nominally, they are qualified, but they still produce far too many false positives. And so you always have to deal with something. They get better over time, and they fix bugs, but they are not perfect by a long shot, and some of them are better than others. And so yeah, and that depends on quite your use cases are looking like. But yeah, and sometimes then you run a tool and you find that far too much of its output is false positives, and it's a pain, but it is less of a pain than having to manually audit all the lines yourself if you only have to audit the lines that it's issuing warnings on, but it's still a pain. So, okay, so we have our full condition coverage tables, which are big, and then we go for modified coverage because we want them to be smaller. And so we limit the choices, and we say, well, if we've got a condition X, so in this case, A or B or C are 3 conditions, then there must be 2 invocations where the result is different for that one condition, and the result of the overall if statement is different. So now we can get things down to 4. If we start with our initial case where A is false and B is true and C is false, and we get a result of false. Then if we go for A is true and B is true and C is false, then we've changed just A. And the result does change. So that's good. So we can test that one. And then we go for another one where A is true and B is false and C is false. And the result is false. So we've toggled the result, and the only difference between the second and third invocations is now that B has changed. And then now we toggle C on its own, and it does change the result. And so we've gone from 8 to 4 cases, which is much more viable. And for 3 different conditions, having to test 4 different cases, not so bad. And as the number of if statements goes up, then the number of cases you have to consider then doesn't go up so much, and that's definitely a big win. One of my colleagues did actually have to get a change pushed through to GCC's mainline in order to get that added to GCOV. But it was important to us, so that was good. It does make it easier if you can track MCDC, rather than having to do the full 100% different condition coverage. And it does mean that the crucial point is that every element in your condition, so A and B and C, all do actually affect the outcome. and avoids you having something which never affects the outcome because it always goes the same way as something else. Now, if you can't construct cases for those 4 lines where just the one thing varies, then maybe your conditions actually are tied together in some way, such that 2 of them are always true together. In which case, then you can simplify the expression and make your code easier to read and understand. So, and likewise, if something never affects the outcome, it's there, but when it's only true when other things actually mean that that's irrelevant, then you can just remove that altogether. So it does highlight if you can't get to 100% modified coverage, then that means that your expressions can be simplified, which is good. And then, of course, we have requirements coverage. This is somewhat important. ISO 26262 says the implemented software unit shall be verified to provide evidence for confidence in the absence of unintended functionality. So this is saying you need to be sure it doesn't do something you didn't intend it to. And obviously, in order to be sure that it doesn't do anything unintended, you need to know what it is intended to do. And so you need to make sure that you've got testing for your coverage, for your requirements. And you need to review your tests to check your requirements, because requirements typically are wordy or with diagrams, and tests are written in code. So you need to review your words against your code and check that they actually do, the tests do what the requirements say that they should do. The output checked in the test is what the requirements say should be the output. So you need to check that. And because fundamentally it doesn't matter it's all very well having 100% test coverage, but if your tests are wrong, the software doesn't do what you want, then it's no good. So you need to make sure that not only are all the necessary cases covered, but boundary conditions, error cases are things that are often less readily thought of, and you need to make sure that those are covered too. And that might be that you go back to your requirements and say, what are we supposed to do when this input value is out of range? It's a measurement value. If it's larger than expected, then what are we supposed to do? Or or what if this bit of hardware reports an error and the things don't work as expected? You've actually got to think through all the cases. Make sure that you have requirements for what things are supposed to do, and then that your tests actually do check the things that the requirements say they do. So someone says, how do you manage the requirements coverage matrix? Requirements to code and what tools are used for that. In-house custom developed scripts using the APIs for the requirements management tools. So in terms of you specify in the source code some identifier that links back to the requirements, and then the tool will tell you that you do indeed have that association, but you still have to actually do the review yourself. There's nothing you can do that will automate that review. Does this test say do what this requirement says? That is always have to be a manual process. But actually checking that there is intended to be a link is something that can be automated. And so we have custom scripts that are doing that. On top of classes, functions, inside functions, and those are on the tests. You put them on each individual test. Obviously, some people put them in other places. People might annotate the class to say this class relates to this requirement, or this function relates to that requirement. We put them on the tests. And the vast majority of our code base is test code. Last time we checked, which admittedly is a few months ago now, then for every line of code, there was approximately 4 or 5 lines of test code. I think I say approximately 45. I think it was like 4.8 lines on average or something like that. And no, because there's so many input cases to cover, and and this is we try and we want to cover things properly, but we still try and minimize our test code. So we have lots of things that are table driven, and here's a table of the input values and the output values expected, so we can rerun things without literally duplicating the tests, or we want to test this with different input types or whatever. So we do try to minimize our test code where possible, but it still ends up being 4 to 5 times larger than the actual code on the test, even though it's often parameterized to reduce the duplication. So it's error handling. What if something goes wrong? And fundamentally, this needs to always be on your mind if you're writing safety critical software. What if something goes wrong? What if my inputs, someone gives me bad inputs? What if I send something over the network and something goes wrong there? What if I talk to a bit of hardware and something goes wrong? And the hardware doesn't do what it says, or reports an error, or whatever. It's a question that you always have to think about. There's a few types of error to handle. Invalid input. If you're writing a function, somebody gives you input that's out of range, what do you do? If you got you're sending messages, requests, calling other code, calling functions, trying to make the hardware do something, and either the other code or the system doesn't do what you intended, how do you handle that? Obviously, sometimes you can't tell other than by the consequences, and sometimes it gives you active error codes. You always hope that it gives you error codes rather than just, I said I was going to open the flap. I returned the error to say, yes, I'd open the flap, but I didn't actually open the flap. That sort of level problem is hopefully something that you don't have to deal with. And obviously there's nothing in code you can do directly there, but as a system designer, you need to think about that. And yeah, if I remember rightly, then that was actually the problem with one of the I think in 3 Mile Island nuclear accident, was that it was some flap that was supposed to be opened, and the light came on to say yes, it'd been opened, but actually the flap was blocked, and so it couldn't be opened. And so all the software said you open it. The software sent the command. The hardware said it was open, but actually it wasn't. And so you need to be thinking of that sort of thing. Is there the potential for undesired behavior? Obviously, yeah. In some cases, you have to think about it as a system level, and sometimes you have to think of it as in your software component directly. And then you have to. There might be logic errors. You just made an error in terms of what you're expecting, what you're intending your code to do. The requirements are clear, and when you coded it up, you made a mistake and you got it wrong. But then actually, if you don't anticipate the potential for invalid input, or you don't anticipate the potential for undesired behavior of other code, then quickly that becomes a logic error, because you should have thought about that. So in some sense, everything's a logic error. And in terms of invalid input, if you've got data coming in, then fundamentally you can't trust it. If it comes from outside your closed bit of software, then you have to imagine that somebody typed it wrong, they got corrupted in transit if it's over a network, or it didn't happen, or somebody pressed the wrong button, or whatever. You have to imagine that the data could be invalid. Okay, and that could have been purely accidental. The user literally pressed the wrong button. They were trying to type in 23 and they typed in 24. It could be corruption in transit, and it could be a hardware fault, which might have caused corruption in transit. It could be that your system's been compromised somehow, and that you're actually somebody's deliberately sending you wrong values. Or it could be something external conditions that are outside your design constraints. You're expecting your software. Your car is only intended to drive on on roads in the UK where temperatures are somewhere usually between -5 and 40 in degrees Celsius. If suddenly you tried driving it in Antarctica where everything's -40 degrees Celsius or something like that, then things might not work as intended. Or if we have a suddenly hot day and suddenly it reaches 45 degrees, then things might not work. External conditions are outside your design constraints. So, okay, so we have some questions, and yeah, David asks some stuff about boundary conditions and input. Who is outside, who is inside, and what level must input be validated? So in public functions, components, or modules, or private functions, or only at software unit boundary. Everywhere is one level, and yeah, I mean, obviously, the anything that's a public interface, then really you have to expect there to be some level of input that you're not in control of. And again, it depends which bit of software you're looking at. Most of the software that I'm working on, as I said at the beginning, is library stuff, and so who knows where our data comes from. So every public function then has to, we have to think carefully about what the input could be. But then if you're a software component that's receiving stuff over the network, then you have to think, where's that data coming from, and verify it. And so yeah, it needs to be validated everywhere, and you need to think carefully. And yes, for your given piece of software, for what you're working on, then it's up to you to decide, what level the different amounts of it's worth investing different amounts of effort in checking your interfaces, your input values. There's something that is 100% coming from something external to your software. If it's user generated or user input, then that's going to need a lot of careful checking. Something that should be coming from something that is also part of your same same system, and therefore if it's gone wrong, then it's much less, then there's something bigger problem, then you can probably rely on that. And obviously it's up to you to decide, where that boundary lies and how much is worth the effort. And which all flows again into defensive programming. It's the same sort of thing. It's like, well, how much effort do you put in? Where is there are trade-offs, and you need to think carefully about your particular cases. In our code, because it's library code, we have a lot of errors, a lot of error checking all over the place, which I guess it counts as defensive programming. Because the consequences of the overall system going wrong are bad. So you want to make sure that that doesn't happen. And that will lead to redundant things. We have checks on inputs, and then our users in the applications then write checks that check. They have checks in their code to make sure they don't give us invalid inputs. So the same thing, it might be checked twice. Hopefully, lots of the cases, the compiler can optimize out redundant checks if they really are the same. But sometimes then they're just there anyway. And yeah, it's something that everybody has to make their own choices about as a development team. Is where the trade-offs lie, and what levels of checking are important for any given thing. But fundamentally, invalid input must be expected when incorporated in the design. So you might validate input, you might log errors, you report errors, you use default values, skip operations. Quite how you handle it, what you do, is up to you and your specific use case. But you need to be thinking about it. What's going to happen when I get invalid input, because you will get invalid input. And then also, you need to understand what other systems do. If you're relying on a piece of hardware to do something, you need to know what it does, what its error conditions are, how it reports things. Same with external software systems. is there a potential for transient problems? Is there potential for faults, hardware faults? If you're trying to send a packet over the network and the network cable physically gets damaged, then that packet is not going to get there. Or it might be that the other system has just gone wrong. Whether that's a temporary thing, cosmic rays tweak the value on a RAM chip, or some water got in and corrupted the hard disk, or whatever, or the hardware was gone rusty and can't move, or whatever. And again, external conditions outside the design constraints. It's too hot, too cold, too wet. Your car gets hit by lightning, whatever. And corruption, whether on static storage or via the network. You need to think about what the potential issues are, how that affects things. But therefore, that undesired behaviour needs to be expected and incorporated in your design. Mr. K says, can we use external open source libraries? And if yes, do they require to be audited and certified? And the answer is, well, they do require to be audited and certified if you use them. And that therefore means that you need to think carefully, because if you put it in your code, then it needs to be audited and certified. And sometimes that means it's just easier not to. And sometimes you can buy pre-certified versions and things like that. So yeah, there's trade-offs. But yeah, you don't have to develop everything in-house, but it does have to be appropriately certified to go on a car. So trade-offs and money. Yeah, you have to check error codes. If verify success, propagate errors, retry operations as necessary, all the things to make sure that everything works as expected and you know when it doesn't. One thing is that about safety critical systems is that they need generally to keep running. If somebody's pacemaker stops working and just freezes, then that's not going to be good. If the steering system in a car stops working whilst you're driving, that's not good. If the drive chain stops working, it's not good. The system as a whole needs to keep running. But the individual pieces of software don't necessarily. And so this is why we have a watchdog. So that if one of the pieces of software that makes up the system goes wrong, then the watchdog will reset the system in some way, to make sure that the system as a whole keeps going. And this is one of the things, things like the various safety standards often have, is that you have to be able to, if something goes wrong, then move to a safe state. And often that safe state is a completely reset system. It's like, okay, restart the system, work out, make the sensors work out what's going on, what the state of all the various bits of hardware is, and keep going from there. Because if you can't rely, if the software stops working, if something is now going out of range, and you didn't, in a way that you couldn't have anticipated, then something has gone wrong somewhere, and you don't necessarily know where. And so this is usually like a piece of last resort. I've detected a problem. I don't know what the cause of the problem is, so I don't know how much I can rely on. So therefore, I'm going to say, "Hey, Mr. Watchdog, reset me." And sometimes that request is as simple as not telling the watchdog that you're okay, because it needs to know that you're okay all the time. And so if you don't say "I'm okay," then it says, "You must not be," and therefore we will reset you. I've certainly worked on those. Every 5 milliseconds, you must trigger the watchdog and say, "I'm okay now." And if you don't reset it every 5 milliseconds, then don't trigger the watchdog every 5 milliseconds. Then it says, "Yeah, you've gone wrong, and must be restarted." And for some things, that's absolutely vital, and that's the easiest way. And other times, then you can say, you can do it the other way. You can say, "Well, I know I've encountered a problem, so Mr. Watchdog, can you reset me, please? And sometimes systems have both options. So there's no, but the whole point is to get back to a known working, known safe state, so that we know what the state of the system is, and we can make sure we proceed correctly from there. And yeah, if you've encountered something that fundamentally is a logic error, and therefore you don't know what the state of your system is, then that's usually the best thing to do. Because the system as a whole isn't in the state that you know how to deal with. It's not something you anticipated. And consequently, the behavior has unknown consequences. Sometimes, those might be unknown in the strict C++ undefined behavior sense, but they might just be, I don't know what's going to happen, and therefore it might be bad. If the config for your pacemaker says a set value that means it's going to be trying to give somebody a heartbeat of 300 beats a minute, then that's probably wrong. But unless you can work out how it got into that state, you probably want to reset it rather than try and do something there. Because something's gone wrong with the data in getting that message. And likewise, there'll be other things in cars that have similar consequences. It's like this whole value is now out of range, so we don't know how we got there. The testing should have picked that up if that was if that's just a straightforward bug. So something has gone badly wrong. So we need we don't know what the consequences are of continuing here. So we'll restart and try again. Okay, so somebody asked about exceptions. Do we use exceptions in our safety critical code? Mostly no, because on one of the platforms, then for example, the compiler says we don't support exceptions. Some of the compilers do, in which case then they're allowed. The coding standards are sort of, well, if you use exceptions, then you must do various things in order to make sure that you're dealing with them correctly, and so they're allowed, but in principle, but in practice, some systems don't use them, and some of our application teams that made a decision that they won't explicitly use exceptions themselves, but they might have to handle things that come from elsewhere. So it's a mix. Yeah. Okay. So back to watchdogs, and obviously we try and eliminate our logic errors through testing and review, and reset, reboot, terminate if a logic error is detected, and we do that with preconditions. Now, something that must be true when a function is invoked, and it's a logic error to invoke a function when its precondition not met. If it says my function must be invoked with between a number between 0 and 5. If you invoke it with -1 or 6, then you really shouldn't be doing that. The documentation said don't do that, and so you've got a logic error somewhere. But if the caller couldn't check that, so it's based on some sort of internal state that you've got, then that shouldn't be a precondition, because you should, if the caller couldn't know. Sometimes that just means you need to give them a function so they know it's safe. Is it safe to call? So they can check beforehand. But sometimes the value might be transient, in which case then it's not a precondition, it's just something you need to handle internally. It's like if you've got a multi-threaded queue and you want to check is there room, or if I check is there room and then I try and push a value, then somebody else might have pushed that last value beforehand, and so now there isn't room. In which case then it's not a precondition that you try, and that it's something you need to check internally. But otherwise you've got a logic error. And so we always terminate our process on violations, because the termination then triggers the watchdog. But then we document them in our function documentation beforehand as well. And fundamentally, this should never be intended. Though we have that precondition check that terminates the process, this is not expected behavior. This is not something you should be relying on for control flow. This is something disastrous has happened, and therefore, we're doing it. It's never intended. But we don't take the checks out in production code. They still run in production code in order to catch those obscure cases when something's gone badly wrong. But you expect that you should pick up all these cases in the testing that you do. Because fundamentally, because it's never intended, something's gone wrong, but we now don't know what, and therefore, this is a bad state, and we trigger the watchdog to keep the system going. So how does this all impact our designs? See, we try to eliminate and mitigate as many sources of error as possible. We favor compilation errors over runtime errors. And yeah, sometimes that's literally just cranking up the warnings. Other times we're treating static analysis errors as compilation errors. And make things correct by construction. So yeah, so crank up the errors. Use -w error. Set your warnings to max and make warnings errors, and then adjust your coding accordingly. Yes, sometimes that makes things a bit more verbose, but verbose means clearer usually. Compiler warnings are the first line of defense against accidental errors. So, yeah, help yourselves out, help your teammates out by setting the warnings on high. And the reason that the compiler warns on things is because they're often a source of mistakes. So don't make those mistakes. And yes, and restructure your code so you don't have to. And it often makes things easier for your teammates as reviewers. Use things like no discard so that you can't ignore error codes. And similarly, accidentally discarding return values can lead to resources being released too soon, or discarding resources and lead to leaks where you haven't trapped it in order to release it later. So yeah, use no discard as in lots of places where you can. And use strong types with abstractions to avoid accidental errors. Use span instead of pointers, so you've got the size is right there. Or use a quantity type, so you can't pass values in the wrong units. You pass the temperature. Oh yeah, well, I thought it was in Celsius, and somebody else thought it was in Kelvin, and then some other bit of code thinks it's in Fahrenheit. But if you pass a quantity that specifies the units, then you don't have that problem. Then, if you've got things which are IDs, then don't just use plain integers. Take the old wrapper structs, a foo ID or a bar ID, so you can't accidentally pass the wrong thing. And again, all these things if they go wrong, they should be caught by your testing. But it's better if there's a compiler error rather than a test failure, because it's just quicker and happens sooner. Use RAII. This is probably my single favorite feature of C++ is deterministic destruction. Use it in order to make sure that things get cleaned up properly. Because it means that destructors always happen whenever that exit happens. All the blocks, however you get there. It simplifies the code, reduces the count of errors. Don't step over those released resources. They don't get skipped. And it doesn't matter whether you're using exceptions or return codes or whatever. It avoids needing to put the explicit cleanup in, and the resources still get released. Dynamic memory allocation can be a big issue. With worst case times, unpredictable timing, fragmentation, and often safety critical coding standards say don't use it. Often you can get around it, pre-allocate memory with optional or containers that contain the data memory directly, or static storage duration. Allocate things on startup. And don't use recursion because it's just waste stack. But you can deal with iterated form and put the auxiliary data in. So you have to think about what your storage requirements are. Don't try and test private members, just make them public if they think they need testing. and complex logic, pull it out as well. There's a whole bunch of small things. Small things are easier to review and easier to test. So when you write safety critical software, lives are at risk. So we follow standards to make sure that everything's good. And we analyze our software to make sure that everything's done, but we need lots of tests. You still need code review. You can't get away from that. But you must think about error cases. And then your design must reflect all these conditions. Okay. So that is everything. It is now time, if anyone has any more questions, we are going to drop over to GatherTown and deal with the questions there. So thank you for listening, everybody.